Okay, today we'll start a single phase transformer, and still we are not completely done with our three phase circuit. I'll do one thing, I'll arrange one special class where I want to discuss a few more problems on three phase AC circuit. We'll do it at the once we complete the transformer part of it. So let us start with the transformer. I hope my screen is visible to you.
Yes, sir.
Okay, so it's you have at least now, once you are almost completed your laboratory class, you have seen what is transformer and what does it do. So let's just revise it. So what is a transformer? It is basically working on the principle of electromagnetic induction, isn't it? And what do we do with transformer? It's a device with which we can change a high voltage low current AC to a low voltage high current AC, uh, and then vice versa. I mean, other way around, without changing the frequency of the supply. So if you want, why do we step up the voltages and we make it low current during the distribution? I discussed earlier in the beginning classes why we go for a very high voltage for the distribution and transmission purpose, not for the distribution during transmission. Why do you go for a very high voltage, keeping the VA constant? Transformer, your total VA volt ampere is remaining constant. So if you step up your voltage, what happens to your current? If your VA,
The
the
current
V
will decrease.
current will decrease. So if current is decreasing, if you transmit at a very high voltage, then what will happen to the losses? If your current is less, then your I square R will be less, right? So their transmission loss will be reduced, right? So that's why we prefer to transmit at a higher voltage. So for that we need a transformer, and when you come from the generating station to the distribution station, and then from there if you want to supply to your house, like the way it comes to our house, and in in our institution as well, wherever for our consumer side, it is stepped down so that we can run our equipments which we are using for our household purpose, isn't it? So for that we need to step down that high voltage again to a lower voltage, I mean the working range. So for that you need to step down your voltage, right? So transformer is an electrical machine which transforms the alternating electrical power from one voltage current level to the other voltage current level, keeping the frequency unchanged. So here there is no transformation of the energy, so it remains electrical energy only. And with the use of transformer you can isolate also your circuit, like it is linked only on the basis of electromagnetic induction. So you are using a magnetic circuit, so your electrical energy you are converting into magnetic energy, and then magnetic energy to again you are getting your electrical energy in the other side, in the secondary. So it transfer electric power from one circuit to another. It does not change the frequency. It carry out this stepping up and down of voltage and current level for the source by the principle of electromagnetic induction. And this is how the two circuits will be isolated. Okay. And once first your electrical energy will be converted into magnetic energy, and then magnetic energy to again you'll be getting your electrical energy. So this is how by a magnetic circuit you isolate between the primary and the secondary, and where the two electric circuit are in mutual inductive influence of each other, then only you can develop the your secondary voltage, right? Because whenever you are sending a current through a primary coil which is alternating, then there will be a pulsating flux within the magnetic circuit. And then when that pulsating magnetic flux is linked with your secondary coil, then what will happen? Your EMF will be induced, because we know from the Lenz's law that E is equal to d psi dt. Okay. So for that in your secondary electric an EMF will be induced. Okay, so now if you use if you keep your decidity as same, because whenever you if you use a linear relationship between B and H, from the H you from the coil you will get your, if you send a current I through the primary coil, then your H will be developed. And if you find a linear relationship, say of unity slope, say if we assume, usually it will be mu into B equal to mu into H. So if you take that linear relationship, then either you can change your mu, with that you can increase your flux density, and then this is how you can improve your secondary EMF, induced EMF. But that is not to a limited way, because anyway if you keep on increasing, if you cannot get that kind of very high permeability, and there is some limitation with that, you cannot keep on increasing your voltage level. So what is the other alternative? If your how your disha is linked, it is n into phi. So if you change your number of coil, then definitely your voltage will be stepped up. When you say if your number of coil for the secondary is more than, it's much higher than the number of coil in the primary, then of course the flux linked with it will change. Or how else you can change the rate of change of flux? You can change your frequency, which we are not doing, because whenever we use for our for a AC supply, we always keep our frequency constant, and for us it is 50 hertz. So we cannot change too much your frequency. You cannot change alter your frequency, and this is how you cannot able to get a higher range of the secondary voltage. Okay, so these are the thing. Based on that, your transformer action is possible, will come after in the subsequent slide it will be discussed. So principle of operation, as I told, it is based on the principle of induction. So here this is your, you are supplying a 2000 volt RMS, and this is sinusoidal. So if you take your linear relationship between the B and H, then your phi will be also sinusoidal. So your d phi dt definitely will get, which will link with your secondary coil. So if you have phi here, this phi will also be, this is what is your H. H is proportional to, it is N into I by L, isn't it? This is your intensity, field intensity, which is dependent on this current I1. So this is I1. So I1 is actually Im1 sine omega t. So if that is your H, and if you find out a linear relationship between B and H, so V will be equal to mu into H. So you can write mu into N1 into I1 by L. Okay, and then what is your phi? Phi will be equal to B into cross section area. So that is the cross section of the, this is through air it is shown, but of course if we use a magnetic material it will be much better. So your flux density will be high, reluctance will be less if you are not using air gap. Then what will happen, your phi will be actually a constant, like this is B into, B is actually mu into Ni by L, and then A is also multiplied to get your phi into I, where I equal to I1 equal to Im sine omega t. So your phi is also sinusoidal. So as it is changing, it is reaching a peak, and then eventually it is going for the zero crossing, and then your negative peak and so on. So definitely if you differentiate with respect to time, your phi expression we can write as phi m sine omega t, where phi m is equal to mu into Ni a L into Im1. So if that is the expression of phi, then your d phi dt will be what? It is phi m omega cos omega t. So if you now link what will be your flux linkage, that n2 will be added to it. So what is your d psi dt? It is n2 into d phi dt. So n2 into phi m omega into cos omega t, or you can write this cos omega t as into phi m omega sine 90 minus omega t, isn't it? That you can write. So now you see that your maximum value of the of your what should I say, secondary voltage should be equal to into omega into phi m. So either you can increase your phi m by taking a more cross section area. On what phi m is dependent? It is depending on ni n1, and then lower the l, less higher will be the value, and then this is your cross section area and this is your permeability. So we have some limitation to increase it magnitude wise here using mu. So what, and cross section area, so what else we can do? If we can increase your n2 frequency, as I told, we cannot change. So if you can increase your secondary turn, then definitely your voltage will be built up. And if you reduce it, just like the here it is shown, primary coil is of 1000 turn and secondary coil is of 100 turn, so definitely your meter reading will be less. So meter here it is showing that actually multimeter, but with there we can see that it is 200 volt in the secondary, because the same phi is linked with it, and we assume that there is no losses through the air gap of the entire flux which is produced. It is linked with the secondary and no other flux is leaking through it. Okay, so based on this, the transformer action we can understand. And now let us go through with the construction details of it. So here we have usually two kind of transformer. One is shell type. From the construction point of view, we can classify them as shell type and core type. So in shell type, it's like this: there will be a central limb. Over it, the primary and the secondary coils are wound over one another, and this is core type. And this is actually not, it is a wrong diagram. This is your core and this is your winding. So this is the core, it is not core. And here you have LV, or over that you have HV, and there will be a insulating material within it. Okay, so this is called core type, and this is shell type, where you have the low voltage and the high voltage. It is given primary and secondary. So there will be certain part of it will have low voltage, and then high voltage, then again low voltage, then again high voltage, and the leads will be taken out accordingly. Okay, and that will be connected with the bushing. So we put your entire coil over the primary limb, I mean central limb, not primary. So this is your low voltage, and over that you have high voltage. In that way also you can do, or you can sandwich also. So it depends on the construction point of view, which will have the maximum efficiency, and lot of other things, lesser losses, leakage reactants, all those things you should take care when you design your transformer. So based on that we keep our winding. Usually it's look like this. This is your core, which is shell type, and there you use lamination of your cold CRGO, cold rolled grain oriented lamination. Uh, this is a steel which will have a particular BH characteristics, which will improve the efficiency of the transformer, and so that the core losses are less. Okay, so we use lot of lamination and we stack one upon the other so that we can get a effective or desired cross section area. Okay, so if we can do that, then your eddy current losses will be less. Apart from that, if you take without lamination, then there'll be a high circulating eddy current, which will responsible for the more eddy current losses, which we do not want to improve the efficiency of the transformer. So that's why we laminate, and then we 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 with the help of lamination we create the core by stacking one upon the other. So here it is shown, it's a core type construction of the transformer. So you can see these are the lamination as you have stacked. So you have laminations like this, and then others like this. So we place like this, so two L kind. So this is how, if we keep on stacking, then your air gap will be uniform, otherwise it not be symmetrical. Okay, so that's how we keep on stacking and we get a core. And on both the limb we put first low voltage winding and then insulation, and then you have your LV insulation, then LV winding, then HV insulation, then HV winding, and this is how your construction of the core type transformer can be demonstrated. And this is the pictorial, it's a rough sketch, I mean schematic diagram for the core type transfer function, core type transformer. Here we have LV and HV. So LV is primary, we can say here, which is of N1 turn, and this is HV, which is N2. So N1 is less than N2, and this is your flux phi, which is passing through this core, and it's a core type transformer. These are the limbs of the core type transformer. Okay, so this is a shell type transformer. It is shown where we put, this is your LV winding, and then you have insulation, then this is your HV winding. Your transformer will be filled up. If it is a higher, it can be air core and I mean air cooled and oil cooled as well. So if you have a high rated transformer, then you use oil as a cooling material as well as the insulating material, and otherwise it is a air core. Okay, so here this is a core type transformer where on the central limb you put LV and top of HV. So whatever is shown here, you are seeing the cross section view of this. So high voltage conductor is smaller cross section conductor than the low voltage coil. Why? Because low voltage side your current will be more for a fixed volt ampere. If voltage is less, your current is more, that means you need a higher cross section conductor. Whereas for the high voltage there will be smaller cross section conductor than the low voltage coil. Okay, because it is of lesser current, due to the lesser current, because if V is high, then definitely your A is small. Okay, so this is how we stack the um, laminations, and then we create a core for the transfer function, transformer. Construction of the transformer from the stamping. So stampings are based on this CRGO steel laminations. Okay, we stack one upon the other, and then this is how we create the develop the core. And the core type, core cross section, limb cross section, if you take, it should be better if you go for the circular one. So this is how you develop with the help of your stamping the circular cross section. Okay, not like your usual round thing, because you are using lamination to reduce the eddy current loss. So that's why you have to stack like this, so that you get a approximate circular cross section. And here if you go like this, you will have a more losses, which we do not want. Therefore we go for this kind of cross section. But this is also possible, we cannot say that it's not possible, but for the better efficiency and depending on the designer, they prefer this kind of cross section of the limb. Okay, so as I told that in case of shell type transformer, HV and LV winding are split into number of section, as you can see here. So you have LV winding like this, and then this is again connected with LV here, and then you complete this winding, and then again you come back here. So this is how you can, this is called interleaved or sandwiched coil, and this is how you can take out your leads for your LV. And for the HV, similar way you can take out your leads and you connect like this. So this is done because of the better there should be lesser leakage and lesser leakage impedance. So kind of winding is preferred due to reduce the leakage losses. Okay, this is the view of the transformer where you have this is the cooling tube. When it is filled with oil. When your there will be transformer in active mode, then of course the oil will, there will be heating effect, and the oil will be uh, I mean, it will go up, it will expand in volume because of the heating effect, and it will come back again through these pipes, and then it will cooled in air and again settle below. So this is how it is cooled, and there will be uh, forcing also. This is naturally cooled, but depending on the higher rated transformer, there will be forced cooling. So we are not going into that details, and we can see these are the high voltage terminal bushing, which will be like this. It will look like this. So these are made of porcelain. This is producing insulation. So HV side, you have the bushings like the bigger one, and the LV side is smaller one. And this is your conservator, where whenever your oil get heated up, it will expand and then it will store in the conservator, and then gradually when it cool down, it will come back to the uh, here. And these are your radiator tube. I told that it is helping us to cool the oil. And in with conservator you have the,
Sir,
yes.
sir, why water is not used? Because it has high specific heat capacity, so it can be better if we
Water
use.
is a water insulating material. We have to insulate na between
Yes, sir. Acha.
between your LV and HV. If you short it, then what will happen? There won't be any transformer action. So if you use water, it is not a insulating material. So there will be always it is a shorted. So there will be a accident actually if you use water, isn't it? There will be a
Yes, sir. Yes,
ex-
sir.
hmm,
Acha.
hmm. Okay, so that's why we use transformer oil, and it is not a ordinary oil. There are certain characteristics which are you from electrical background, electrical stream, or your
No,
stream?
sir. I am from EC.
EC. Anyway, you may have to learn. I don't know. A little bit definitely will learn, but for you, you don't have to go in that details, because oil is used only when you go for a very high power transformer. But for electronic circuit, there should not be that much. So very for you, if you use the air cooled transformer, that is okay for you. Anyway, so there are certain characteristics with which we can classify the transformer oil. You cannot use any oil. So transformer oil is a specific, it should have specific characteristics, insulating property, and then other things as well, and which I am not going to discuss because it is beyond your the scope of this course. So what happens, there is another thing, when there will be expansion, then it will go to the conservator and then fill it. So whatever air is there in the conservator, it will go out because of this expansion, and then when it will cool down, then it is that expansion will go off, so it will condense and it will come back again into the tank of the transformer. Then what will happen, the air from outside will go and fill the gap. So if we do not use the breather and the silica gel over here, then all the moisture from the atmosphere will go inside the transformer, and then that will reduce the dielectric power of your transformer oil. So your insulating property of the transformer coil will be oil will be deteriorated. So which we do not want. That's why we use this breather and silica gel, which will remove all the moisture content in the air, so that your transformer oil health remains fine. Okay. So working of the transformer, as we were discussing, when current in the primary coil changes, being an alternating in nature, it's there is a changing magnetic field is produced, and this changing magnetic field gets associated with the secondary through the soft iron core. You can use soft iron laminated core. You can use CRGO for the soft iron core also. If you use that will work. But usually for the standard transformer, we use cold roll gain oriented steel, so that your hysteresis losses is less. Otherwise it will be more. Hence the magnetic flux linked with the secondary coil changes when it is linked with when the flux is linked with it, and if that is changing, then definitely you will get your uh, you will get your induced EMF in the secondary. So actually what happens, you have your BH curve like this. So there will be, it's like this. So how sleek it is the curve, lesser is your loss. Okay, so if you use a sinusoidal signal, then due to the hysteresis effect, your and the non-linearity, it is not always linear. After certain point it will have a non-linear characteristics. When you go to hit your knee point, then what will happen for sinusoidal current I, which is proportional to H, you will get a flux which will look like this. This is your phi and this is your I. So then what will happen, it will have lot of harmonic contents, and because of that there will be losses. So if you, that is responsible for the core losses, and if you take a bigger area, then this core losses, it will have a more distorted from the sinusoidal, so it will have more losses. But if you use a linear thing, if you get a BH curve which is very small like this, I mean your area is very small, and if you use sinusoidal H, I mean your field intensity, you will get a flux density which is approximately sinusoidal. So then there won't be much harmonic signal present in it. So if harmonics are less, then your losses will be also less. That's why we go for the CRGO based uh, core, so that your hysteresis loss is less. And we go for the lamination, because if you laminate it, then there won't be high circulating eddy current, and if eddy current is less, then your it's like this. If you take a bigger block, it will have a high eddy current, high circulating current. But if you laminate the thing, then there will be small, numerous but small. So then your eddy current losses will be also less. Okay, so that is why we go for CRGO and the laminated core. Okay.
Sir, that point couldn't understand what harmonic will be there in the.
Okay, let me clear it. If you have a signal like this now, if you have a fundamental signal, this is your fundamental sinusoid, agree na? Then if you have the third harmonic, then if this is omega, then third harmonic will be 3 omega, that we call the third harmonic. Then if we have fifth harmonic, then it's a 5 omega. So if it is a third harmonic, then within one cycle it will complete 3 cycle, I mean 3 half cycle here. So eventually like this. Okay, so this is your third harmonic. Now, if you add them up, then how does your waveform will look? This is your fundamental, and then if third harmonic is present, if you add these two, your plot will look like this, isn't it? Instead of sinusoidal, it will look like this. So if you have a distorted waveform, distorted means non-sinusoidal waveform, you can split it in terms of harmonic signal. So if those harmonic signals are present, because of that, this harmonic won't contribute in obtaining your output. So then what will happen? This will responsible for the losses in the circuit. Okay. So which we do not want. We try to make it free from the harmonics for the AC circuit. So if you understand this much, that is sufficient for you.
Okay, sir.
Okay, so whenever if you get a step signal also like this, na, you can get a lot of harmonics within this. One is like this, another is third, then you have fifth. So those things will be clear when you will learn the Fourier series analysis. Maybe in your next semester when you learn in maths, you have Fourier series analysis. So there you will see that you will be given some odd function, even function, which you can represent in terms of a some summation of sinusoids. Okay, and with different frequency. So that is actually called harmonics. Okay, so this is the schematic diagram of a single phase transformer, and here you have two or more winding coupled by a magnetic core. We are for the representation purpose, we are not drawing the coil one over the other, but actually, as I told, practically it is not like that. Your n1 n2 will be n1, half of the n1 here, half of the n1 there, half of the n2 here, another n2 here. That will reduce your losses, because if you put here only, or whatever phi is produced in the core will be linked well with both the coil if you split it like n1 n2 both here and there. But for the sake of clarity in the sketch, we are drawing like this. Okay, so this is your supply, this is the current which will be drawn by the primary coil of n1 turn, and then that will produce a pulsating flux or sinusoidal flux, we'll say, in the core, and that will be linked with this n2 coil with n2 turns. So n2 into phi will be your psi, so your psi will be actually n2 into phi m sine omega t, and then you get your E2, which is equal to d psi dt, or Ka d psi dt, whatever it is. So that is your induced EMF. And now if you add a load, if you connect a load here, then that load will try to draw current from it. So initially when you are not connecting any load to this, then what happens, it will the I1 current will be drawn, which is just because of developing the magnetic circuit, developing the flux on through the magnetic circuit. This is your magnetic circuit. Okay, so this is responsible for connecting your coil 1 with your coil 2. Okay, and whenever you do not have any load, then what is required, only current is required which will create this phi, and for that negligible current I1 is required. But whenever you connect a load in the secondary, that load will demand current to, so for running it, so that will drawn by the uh, this supply itself, because it is connected with the magnetic circuit, and through this your I2, if you are drawing more, then definitely that has to be supplied by this source, and that I1 is doing. So I1 will be having two components, then one is your magnetizing current plus your rated current, which is demanded by the load. Okay, so this is how these things we should keep in our mind when we'll draw the phasor diagram for it. Okay, and what are the assumption we make? These are the ideal transformers. So this is practically not happening, but this is the ideal transformer, and for that we assume that there is zero leakage flux. That means flux produced by the primary and secondary currents are confined within the core, and it is there is no loss through the air gap and all. Okay, and the whatever flux is produced is there in the circuit, that is completely linked with the secondary, and it is not going anywhere. Okay, the winding have no resistance, which is very impractical. Practically windings will be having some resistance, but we assume that there is no resistance. Okay, the core has infinite permeability. That is also not possible, because reluctance of the core is zero, it is never possible, but it should have a higher permeability. Negligible current is required to establish magnetic flux. So if you have infinite permeability, that means zero current is required, so which is not possible. What is possible is very small value of current is enough to set up that flux if you have a low reluctance. You know what is reluctance, right? What is the expression of reluctance? So if your mu is high, your S is less. That is why when there was a air gap, your reluctance was more. When we were discussing about the magnetic circuit, we found this. So if you take a very high mu circuit, magnetic circuit, then that reluctance will be less. Then very small current is required to establish the magnetic flux through the circuit. And lossless magnetic core, that means there is no hysteresis loss and no eddy current loss, which is not practical. What we can do, we can go for such material which will having a lower hysteresis, as I told, that sleek BH curve like this. You have this and you have this. Out of these two, this one will have the lesser hysteresis loss. Okay. And eddy current, to reduce eddy current loss, we use lamination. If we take the lesser cross section, if you stack it, then of course your circulating current through the laminations will be much lesser, and then that will reduce your eddy current losses. But practically, lossless magnetic core is not possible. So with all this assumption, we get the ideal transformer, but practically these are not possible. What we can do, we can aim for reducing this as much as possible. So now this is your transformer action. This is the EMF equation for the transformer, which is very important for you. This is the main thing which you should grasp well. So this is your, you have seen the schematic of it. This is your E1, N1, I1. V1 is the supply voltage, and E2 is the EMF induced in the coil. E1 is the EMF induced in the primary coil, E2 in the secondary coil, and I2 is demanded by the load. So whenever there is no load connected, we simply just connect your transformer to the source and we apply a switch on. Then what will happen? These are the things which we already discussed. So N1 is the number of turn in primary, N2 in secondary, and phi m is the maximum flux in core in Weber, which is flux density B maximum into A. F is the frequency. Okay, so we can find out like this, as I have it is done in a different way, which I do not prefer. Let me solve it like the way we have solved. So if we apply a sinusoidal voltage V1, and that if it is connected with your uh, um, primary coil, then there will be a uh, current which is I1, which is Im sine 2 pi f t, because omega equal to 2 pi f, it is given frequency in hertz, right? This is your I1. What is your H1? It is N1 by L into I1. And what is your B? That is equal to mu into H. So you can get mu into N1 by L into I1. So this is Im1 sine 2 pi ft. And then this is your phi. Okay, so the whole thing is your phi m. So we can write it as phi equal to phi m sine 2 pi f t. Okay, so if you get your phi like this, then what is your psi? Psi is linked with the coil N2. Coil 2 is N2 phi m sine 2 pi f t. And now you find out what is your d psi dt. So this will be nothing but N2 phi m 2 pi f into cos 2 pi ft. Okay, so now if you look back, it is nothing but if you put the value of this, your RMS value, if you want to find, this is the instantaneous value E2 for the secondary, which is what, which is uh, um, 2 into 2 pi, sorry, 2 pi into N2 into F into phi m. So what you can write, it is in N2 into phi m into F into 2 pi. If you want to find out the RMS value, you should divide it with root 2. So root 2 into pi will ultimately give you 4.44. So you can see the EMF induced is actually, it is 4.44 into F, which is frequency, then N, which is your number of turn, into phi m, which is equal to Bm into A, where A is your cross section area, that remains the same. So it depends on the maximum flux density, it depends on the number of turn in the coil in the cross section area, and this 4.4. So now Bm, if you want to express, I don't know whether it is given or not, no. So if you want to express that in terms of Bm in terms of I, then there you will find your mu. Okay. So this is how you can get your expression, EMF equation for the transformer. And I won't suggest you to read through this from the book by Thereja. I'll do one thing where it is well given. It's a given well in the book by P.S. Vimra, that I'll scan and share with you. It will be better for you then. So this is the phasor diagram. In the next class also I'll continue with the phasor diagram. For the time being, for the ideal transformer, let me explain a bit. So this is your voltage, and whenever you have the resistance R equal to 0, so it will have a AC circuit and it's a coil, so it is a having the inductance, right? So as it's a purely inductive circuit, it will V1 will I1 will be lagging V1 by 90 degree, as we can see. Now if your there is no hysteresis and eddy current loss, your here for this particular case, when there is no load connected, your I1 will be equal to your Im, which is your magnetizing current, which will produce a flux phi. So I1 is equal to your Im, that will produce the flux phi, which is in phase with I1. And then what is your I2? I2 is actually, it is again it will be like this is your E. First you should get E2, then only will get I2, and here I2 equal to 0 because you are not connected any load across it. So what is your E2? Your E2 will be equal to that d phi dt. If you do d psi dt, if you do, it will again lag Im by 90 degree, right? E1 lags Im by 90 degree, that is phi by 90 degree. And E1 is developed in such a way, follow the Lenz's law, so it will try to oppose its cause. That is the inductive effect, you know. So your E1 polarity will be in phase with E2, right, as you can see here. So your V1 minus E1 by, if there is any leakage resistance reactance, that you can put it, which will be equal to your I1. That is why it is put in the other side. And E2 you can get from here, because whenever you get cos of this, so it will be 90 minus sine 90 minus this. So then it is lagging phi m by 90 degree, your E2. So that is why here also E2 is lagging phi by 90 degree. Okay. And now if you can measure the voltmeter reading here, this is your output voltage. This is the no load output voltage, because you have not connected any load across it, so there won't be any loss here, and you get V2 is equal to your E2. But whenever you consider the leakage and whenever there will be load, so the phasor diagram will completely change, and you will get a different phasor diagram, which I don't want to discuss today. Maybe in the next class I'll discuss about the phasor diagram of the transformer, which is like this is with no on no load, and you have the core loss component. This is like non-ideal case when you have the core loss component, how your phasor diagram changes. And then what is your I0, what is the current required, which is the phasor sum of Im and Ic, all those things. And whenever there is a load, then what happens, how your I2 will change, then if I2 changes, how your I1 changes, which is I0 plus I2, all those things, I2 dash, that component. And then depending on the nature of the load, if it is a unity power factor load, then how does it look, if it is a lagging PF, leading PF. So based on that, your phasor diagram will change, and then only we can move forward for the equivalent circuit. Okay. So I conclude here today. Do you have any question? Okay, so if you do not have any question, then I close for today.